everyone. This is our project on magnetophoretic transport. This project investigates the motion of suspended magnetic particles in a viscous fluid under the influence of an external magnetic field. And so we tested 6 different fluids, tracked particle motion using video analysis, and we drew conclusions from our results to prove our hypotheses. Our investigated phenomenon is magnetophoresis. When ion particles sit in a fluid near a magnet, we have 2 forces competing. The magnetic gradient force pulls them forward, while the fluid's viscous drag resists that motion. In our low-velocity small particle system, we have a creeping flow regime, and so the force balance simplifies to the magnetic force equaling the drag force. Our experimental setup used a 100 by 100 millimeter polystyrene Petri dish, shallow enough for quasi-2D motion analysis, and then 52 magnet was fixed outside the container. Iron-filling particles were placed in the fluid system, and finally, a fixed overhead camera recorded all particle motion. So here is the schematic of our experimental setup. The coordinate system is fixed to the Petri dish. The x-axis points towards the magnet, while the y-axis points upwards, consistent across all trials, and the origin is set at the reference particle's initial position at initial time.
In this experiment, we first prepared 6 different fluids with distinct dynamic viscosities. For each trial, exactly 40 ml of fluid was poured into a Petri dish and a small amount of iron fillings were added. A strong permanent magnet was placed outside the dish at a fixed distance of 13 mm from the edge. A camera was mounted above the setup to record the particle motion from the top view, giving us clear 2D data in XY plane. These videos were then analyzed using ImageJ, where we tracked 3 particles. One is at the top, one is in the middle, and one is at the bottom to capture velocity behavior in different regions. This slide shows us photographs from the actual experiment runs, one for each fluid tested. From ImageJ, we exported position and time data, specifically x, y, and time for each frame. Using this data in Excel, we calculated particle velocities frame by frame to obtain accurate velocity profiles over time, and then computed average velocities. To ensure reproducibility, we performed 3 trials for each fluid and compared the result across all trials. All slides shown here include images from the experiment runs and examples of the particles tracking in ImageJ.
Here we have the velocity profiles for representative particles in each fluid. In water, particles accelerate very quickly, reaching the highest velocities. This indicates low viscous resistance, so motion is dominated by inertia. In oil, velocities decrease significantly compared to water. The higher velocity increases the drag, leading to a slower and smoother motion. In liquid soap, the motion becomes more damp and irregular, and the viscous resistance dominates, limiting the particle acceleration. And the condensed milk shows noisy and variable velocities. This is due to the heterogeneous nature, which affects the particle motion. In glycerin, the motion is extremely slow and highly damped. This indicates a strong viscous regimen, where drag dominates completely. With the corn syrup, this one shows the slowest motion, and the particles remain nearly stationary, confirming the strong viscous damping. Here, we compare the velocity profiles of representative particles across different fluids. The top particle shows the strongest separation between fluids. In water, it accelerates rapidly, while in viscous fluids like glycerin, condensed milk, and corn syrup, the velocity stays orders of magnitudes lower. This confirms that viscosity dominates the initial response to the magnetic force. The middle particle shows the same viscosity control trend, but with smoother profiles. Water still leads by 2 orders of magnitude, while high viscosity fluids remain near 10 to minus 2 to 10 to minus 3 centimeters per second. This indicates that deep in the fluid slightly damps fluctuations but preserves the same hierarchy. The bottom particle moves the slowest overall, especially in viscous fluids. Water still shows the fast acceleration, but all other fluids remain tightly clustered at very low velocities. This shows that particles deeper in the fluids experience a stronger drag and weaker magnetic influence.
This slide shows Reynolds number as a function of time for each fluid. Most fluids operate at Reynolds number less than 1 for glycerin, corn syrup, condensed milk, and liquid soap. This confirms that viscous forces completely dominate over initial forces. This means that the Stokes law is valid. Water has such low viscosity that even the slow particle motion produces a Reynolds number significantly greater than 1. This means that lower the viscosity, higher the Reynolds number, and higher the viscosity, lower the Reynolds number. This means that the flow is creeping flow and the Stokes regime. This slide gives us the full Reynolds number versus the time curves for all 6 fluids plotted together. Notice the dramatic separation between the water and the rest of the fluids. This graph also shows that for viscous fluids, the Reynolds number stays nearly constant and increases only over time.
From our experiment data and results, we confirmed the velocity profile is unsteady and proved our primary hypotheses of particle velocity evolving with magnetic field gradient strength, and we also showed the particle velocity is dependent on the viscosity of the fluid system. Thank you.